All right. Probably should have done that before I started. Let's make sure everything's coming through all right. Man, apologies. All this I should have done prior. Ooh, got some baggy eyes today. Look out. All right. Everything's looking good. Let's pop out that just in case. Always to be safe rather than sorry. All right. So today, a couple things off the bat. I actually decided to pick up a new resource. So all my resources up until now have been some form of digital or something that I'm writing down myself, like notes I'm taking or flashcards I'm creating. Labs from Packet Tracer, Udemy, CCNA subreddit, YouTube videos. Nothing. I haven't been reading anything though, so all my other certificates, I had really great books that I read through. And so I decided to pick up Wendell Odom's official cert guide today. It's not here yet. It's coming in the mail. I got it off Amazon. But because of that, I also have access to the Kindle, some of the Kindle, so I can get into the first parts of it. But this was just a representation to show you what I got today. And again, this is just to add a different perspective, of course, because it's Wendell Odom. It's also the official cert guide, so this is the one that Cisco like really touts as having the all the information that you really, maybe not all the information, but the most accurate guide, right? Because it's the one that Cisco endorses. But really, it's just about reading. I just wanted to add another way of getting the information into my brain. It seems like the more ways I add in, the better it sticks, the more paths to those neurons create, or however the brain works, right? Like, it seems to help. Also, I'm not great at sleeping at night, so having one of these thick technical guides next to you in bed, it puts you up fast. So benefit to that is these bags under my eyes are probably going to disappear pretty soon, hopefully. And the other thing is, for some reason, or I'm guessing it's pretty logical, the stuff that I intake right before bed, I seem to shift into long-term memory and short-term memory. It just seems to stick better. And I'm sure that has something to do with how the brain sorts your day or something like that. But yeah, so right now, having a book to read right before bed, or leading into the night, taking yourself away from screens, getting on a book, it takes down your brain step by step. But also, as I get closer to the test, I love to take that time before bed and go over the flashcards that I'm having the most difficulty with. Because again, for some reason, well, not again, for some reason, logically, it makes sense that the stuff that you practice right before bed is just going to shift better. And maybe it's my confidence in that, or maybe that's really how it works. But yeah, reserving that time for flashcards before the test, like leading up to the test when I've already got all the information, and I'm just trying to shift it into my memory and make all the connections that are necessary to make to really understand it. That time before bed really seems to be powerful. That's not to say that I don't study all through the day. It's just to say that's where I keep like the material that I'm having a hard time engaging with or memorizing for whatever reason. So yeah, that's just a resource update. I'm just adding another resource. I don't. I mean, it's 2 books and a bunch of labs, and that sounds like a lot, but I devour these books. Like, I may not understand exactly everything I read, but for some reason, I'm just able to devour them. So it's not fun, but yeah, I'm actually kind of looking forward to it in a strange, weird way. Also, something else that came out today. the FCC just approved a $50 month subsidy for low-income households to get high-speed internet, plus a $100 discount on a computer. So I just want to highlight that because I just think it's really, it's a way of showing how important, not just networking, but of course networking is, like how this is technology, and not just in the programming dev side, but technology at large is growing. Like if everyone has better internet access, that's just going to grow the pool of people who can participate in like help desk activities and things like that. And being able to have your CompTIA A plus or Networking Plus or even your Cisco understanding is just going to help grow that job pool. And it's also going to expand what the country can do. Like, you know, hopefully there'll be like a better understanding of how important networking is. Because I know that from my experience, I've lived a lot of places in the country, in the United States, and it certainly is a lot easier. It's never easy. It's not easy to get an IT job, but it's easier in bigger cities, big cities, larger, like millions of people. There's just, for whatever reason, there's always some kind of IT network there, whether it's help desks or networks, data centers, actual software stuff. Like they're just found in the bigger cities. Like small towns, they just don't have it. And part of that is probably like infrastructure. Like not everyone even has high-speed internet necessarily in these smaller towns, but a lot of it is also like mindset. So hopefully this kind of like, you get more people access, there's more demand for actual like jobs and businesses that cater that kind of stuff. So hopefully some of these smaller towns around our country are able to update their infrastructure in a way that allows for like small network companies or small ISPs, stuff like that, to start up around the country, because I think that'd be beneficial to everyone. So this is just kind of a cool way to highlight it, because it seems like the government is also looking to help people get on the internet, help people get computers, help people understand and play with technology. Like the internet's not all great, but there's some pretty amazing things you can do with it. So, you know, hopeful. Let's get to actual Cisco information. So yesterday we talked about some different routing protocols, and how some of them are kind of outdated, while others are more commonly used, and some are better but not commonly used just because of how they were kind of shifted into the market. So Ospf is the most commonly used, so that's the one that we're going to go into more detail on. So we can remember from yesterday, the first thing that happens when you turn Ospf routing onto an interface, when you switch that interface to have Ospf routing capabilities, it's going to send out a hello packet, right? Actually, it's going to send out hello packets. We'll figure that out a little bit later on. But so Ospf enabled interfaces send out help packets, send out by default every 10 seconds, right? So every 10 seconds, the Ospf interface is going to send out a hello packet. And you might think, like, if you already have a connection, if you've already established an adjacency on that interface, why would you continue to send out these hello packets? That seems like detrimental to the bandwidth of the network. Well, it's actually also used as a way to determine that that router is still capable of receiving information, right? So like if you continue to send out hello packets and at some point you no longer are getting acknowledgments, you know something's up, right? So it's a good way to monitor your network. Monitor specifically within the OSPF routing protocol. So all those interfaces that are enabled there. The only time this doesn't happen is when that OSPF enabled interface is also set to passive, right? So it's not access, but it's a passive. And remember, we would use that if we're so if it's a router that's on the edge of the network, or if it's a router. What else did we say? If it's a route that's going somewhere that doesn't have any, there's never going to be return traffic. So like a loop back is another time we'd use a passive interface. So again, because it's a passive interface, hello packets aren't going to go down it. So it doesn't matter, right? So it's just saying passive. It's you don't need to worry about this stuff on this interface. So another interesting thing about the hello packet is it's not a unicast, right? So it's not sent out on a one-to-one basis, right? Because it doesn't know where it's going. So it's sent out multicast, and it's sent out specifically on this IP address. So it's multicast to 224.0.0.5. And that's neat because that means all other OSPF routers, that's not a good way to put it, all other OSPF enabled interfaces on routers, because it's not the router, right? It's the interface. That means they're able to listen for that specific IP address, right? So when you have an enabled interface, that means it's automatically tuned into 224.0.0.5, because that's where it's going to pick up its hello packets. So I think that's pretty neat. It kind of helps you understand the process a little bit better. And it also means that when you're for whatever reason, if you're taking a packet apart or looking into your network to see what's going on, you can, if you see traffic on that IP address, you know what it is. You know it's OSPF packets. More specifically, it's likely a hello packet, right? And if you have an OSPF enabled interface, but for whatever reason it's not picking up that IP address, there's an issue with the network, right? Somewhere in there. So it's helpful for troubleshooting to know what the IP address is and what the actual data is that's going to be contained in that. So let's get into that. What is contained inside of a hello packet? Turns out a lot. Like a lot of these packets, there is a lot of information kind of tucked into these headers. So the OSPF router ID is going to be the first thing that's tucked in, and this is how it's like the name, right? So it's going to be in the form of an IP address, and hopefully it's a loopback address. Hopefully it's a passive loopback address, because that can't go down as a logical address. But if it's not a loopback address, then it's going to choose the highest IP address on the interface associated with that OSPF interface. So it's going to be on that interface. The highest IP address is going to be that router's ID. But hopefully it's a loopback. Hopefully it's a passive loopback. But irregardless, that's going to be the first bit of information. But hopefully this is a passive loopback. The next thing is going to be your hello interval timer. This is defaulted 10 seconds, right? We said that earlier. Every 10 seconds, it's going to send a hello packet, but we can change that. So we can make that faster or slow. We can make that more common or less common depending on how quickly we want our devices to update. Also, how fast we think our network can handle. Because if you set that at like 1 second, but your network starts to experience delays because you have a bunch of traffic on it, then you're going to start having problems because it's going to think right here, dead interval timer is 4x, so 4 times the hello interval time. So whatever you set as your hello, your dead interval is going to be 4 times that. So if it's 10 seconds, then at 40 seconds, if this interface does not receive a hello transmission from its adjacent buddy, it's going to say, uh-oh, I think he did. I think that router over there did. And that's going to cause it to make a bunch of decisions. It's going to change its routing tables. It's going to make updates, LSAs, LSA acts, if you remember all that stuff from yesterday. All those different abilities, all those different protocols that are, what would it be? So Ospf is the protocol. So all those packets, I guess, all those transmissions it sends out to keep the routing protocol working. The next thing is going to be a subnet mask. So this is just going to be, whatever that subnet mask is for that network that it's on. Router priority, I'm not entirely sure about this, but I think this has to do with areas specifically. Maybe not, but so I have to look into this. But I'm pretty sure this has to do with areas, and we'll go over that in a second. So it's also going to include, here's a real good piece of information. Neighbors. So super important information. It's going to be like, hey, you know what else I include? I include all that information that's actually important to us. What the basis of all this, the actual network. The next thing is the area ID, and the area ID is interesting. So as long as you're not like a really large network, you're just gonna, you're gonna set it to one thing, and it's gonna be one thing across your entire network. Typically, you're gonna start at 0. Small networks, area ID, not a big deal. Just set it to a single number and keep that. However, large networks, the area ID is a big deal, and we'll go into that a little bit later. To be discussed later. The next little bit, and this is all just, again, this is just the hello packet contents. So this is just, it's going to have DR and DBR IP addresses. And this is specifically if it exists. So this is not necessarily going to be something that's, there's going to be a slot for it in the packet, but there may not be any data in there because not all networks are going to have this. It is necessary. It's something that's needed for multi-access segments. And again, this is going to be discussed later. So now it's just kind of like setting out a agenda, I guess, in part because some of this is I'm discussing in completion. Some of it's just like later. So the last little bit of the hello packet is going to be the authentication password. So when you first set up Ospf on the interface, when you first set up Ospf profiles, you can enable a passphrase, a password. It's it's a good idea to do that. This keeps people from connecting just unnecessary routers to your system that don't have, that you don't want on there, malicious activity or just mistakes. That kind of stuff can bring down a network real quick. So authentication passwords are good for not just security, but for network stability. But if it's not configured, it's gonna be a slot within the packet header. But again, it's just not gonna be filled with data. It's just gonna be empty. But it's good to know that it's a possibility, and it's also just good practice to do it. So in order for two routers to become neighbors, oh my gosh, right? Like, we're just talking about hello packets. Like, isn't that all you need to become neighbors? No. Turns out there's some other important information. So you have to be same IP network, subnet. That kind of makes sense, right? Like, if you're not in the same IP network subnet, then, well, I don't know. For some reason, you can't be neighbors. I mean, you're routers, so you should be able to route between different networks, but no, you can't be neighbors because it said so. And ping, come here. Hey. All right, 1 second. I'll be right back. Hey. Oh, okay. You're okay. Thought I heard something. I don't know what I heard. I don't know what I heard. Oh. I apologize. That kind of threw me off track. I gotta watch after my dog, though. She does like compulsively chew on her paws sometimes, and it gets nasty. It gets bad for her. It's bad for her health. She takes advantage when I have headphones on. She's smart. So I was going over same IP network, and now I was confused, and some things are just some things until you understand them in better detail. The hello and dead interval times. Come on, you can spell. Timers must be identical. So we were talking about how you can set a different hello interval if you wanted to. And the dead interval, you don't set a default. It's just 4 times whatever your hello is. So if those are different for whatever reason, you set it, you default the hello timer on one router and you set the hello timer on the router that should be adjacent at a different time, they're not going to sync. Like, they just won't do it. They won't be buddies. They won't be adjacents. So that's important to keep in mind. If you change something on one, you got to make sure that its buddy has that same interval. So coming back to area IDs, the router interfaces connecting the two routers must have the same area ID. So this beginning part is the same for all of them, right? We're always talking about the routing interfaces because Ospf is enabled on those routing interfaces. But it is also important to just kind of keep it in mind. So if you're writing something down, just include it. But we're always talking about that with Ospf, unless we're talking about like the profiles that you create in the very beginning. But even then, like, just, memorize it. Type of area. Okay, so real quick, let's go over area ID just shallowly because we're going to go in more depth in a minute. But so like I was saying, small networks, they just kind of default it to whatever that number is. Most use 0. So as long as the interfaces both have area 0, you good to go. But if one's area 0 and the other one's area, X can be any other number, they're not going to form adjacencies. They're opposite areas, or they're not congruent areas. Must equal same. So again, authentication password, if used, because it doesn't have to be, must be identical. That makes sense. I mean, that one out of all of them makes the most sense, right? Like if you have the password on one interface is dog and the password on the other face is cat, they're not going to look at each other and be like, bestest buddies. No, that's got to be the same. You got to share that password. You got to have the same password. Don't share your passwords. Getting a little kooky. Not gonna lie, getting a little kooky. OSPF on multi-access segments. So we talked a little bit right here. We talked about DR and DBR IP addresses. This is part of the hello packet contents, but it does not necessarily exist on all networks. So now we're actually going to talk about what that is. Is that the interface? Oh, I got to read up on my notes because I confused myself. OSPF on multi-access segments where there can be multiple routers. That doesn't make sense to me. One router would be necessary. Oh, okay, yeah. So multi-access segments. Let's see. I haven't pictured in my brain what that really means. But now I have. Or now it just came back to me from watching all those lectures. Multi-access segments is so up till now we've been talking about a router interface directly connected to another router interface, right? Like a one-to-one connection, super simple, router to router. We're buddy, we're adjacent buddies. We're sharing this network, right? Like that's pretty simple. Multi-access segments is when it's a router attached to a switch, and then that switch is attached to a router, is attached to a router, is attached. So that switch is attached to multiple routers. None of these routers are attached directly to one another. They still want to be able to run this OSPF. They still want to be able to build out this network. However, you don't want all four of these routers sending out hello packets all every 10 seconds. Like it would be because this is just a very small understanding of what a large network could be, right? Like it could be, you can starfish this out pretty big to the point where you just have a significant portion of your bandwidth would be hello packets constantly going out. So what you do with these multi-access segments is this is where you can designate DR and DBR. So these stand for check it out. Once you understand what these stand for, so much easier. DR is designated router, also referred to as a master. I mean, I don't know. Tech people, I talked about this before. They got big heads when they talk about stuff, man. Why would you call this a master? There's so many better names, and you don't want it. They call the other ones slaves. It's like, come on, guys. Backup router. Okay, so the DR is a designated router. It's the master router. So out of this starfish pattern, out of this multi-access segment, one router is going to be the router. It's going to be the one that's in charge of all the other routers within this multi-access segment. There's also going to be a DBR, and that's the designated backup router. So we always want to have some kind of redundancy in our network, right? We want to build in redundancies. So if one router goes down, another router can pick up the slack. So that's why we do this. We have the designated router, but for whatever reason, the interfaces go down, the power surges in that building. We want that designated backup router to be able to pick it up so that our entire network doesn't seize up because this multi-access segment no longer knows who's in charge and either starts firing hello packets all over the place or so. I don't know exactly what would happen yet. I'm not that versed in it, but it doesn't sound good. So we got the backup. So there's a lot of things going on with these. designated as the leader of this multi-access segment. I like the sound of that. Not sure if leader is the right word, but we're gonna go with it. So the DR, so how do you know what's the DR and what's gonna be the DBR? Is that something we designate as network administrators? Kinda. It's actually designated by router priority. So within that multi-access segment, the router with the highest priority will become the DR, designated router, and the one with the second highest priority will become the DBR, the designated backup router. I think we all know what I'm talking about. Kinda. Here's the thing. What are routers default at? Turns out every router is 1. So that doesn't help us. if every router defaults to 1, there can be no DBR because they are all equal. So that is why network administrators, you and me, man, how did I screw all that up? Have to. I'm sorry, I'm so kooky today. Default. So that's why we have to change these. Oh, wait, no, wait. So, okay, I got a little ahead of myself. Apologies. Every router does default to 1. However, if every router on the network defaults to 1, then it actually goes to decided by the highest router ID. Loopback, hopefully. So loopback, hopefully, is a touchback to a couple days ago when we learned about loopback. You don't actually need to know that right now. But decided by the highest router ID. So again, the router ID is going to be the highest IP that interface services. So there's always going to be one. So then it's going to be determined by IP address. I don't think it's necessarily a big deal. You know what I'm saying? Like, I think allowing routers to designate the DR and the DBR via the router ID is totally cool. Like, I don't see a reason for us to get involved in this. And it seems like, based on what Neil Anderson was saying in his course, that's the going way to do it. Like, we need to know how all this stuff works, but I don't foresee a reason for us to get involved in changing. Well, I guess just by whatever you designate. Like, so if you do use a loopback as a router ID, just know that the highest loopback you use is going to be the designated router within that multi-access segment. So, you know, this goes back to, we talk about this stuff like it's happening on the fly, but when you're making changes or when you're building a network, like, you got to think about this stuff well in advance so you understand it, right? Like, and this is a good reason why, because if you're building out a network and you do have multi-access segments, then you're gonna want to, like, I think like, we aren't necessarily looking to do this, but I think if you're building out the network, then you are going to want to know which one's going to be the designated router, the designated backup router, and you're going to want those to be specific ones based on how you're building your network. So knowing that and knowing that you can designate those by the router ID, it's pretty easy to build out your network that way, you know? So good to know this stuff. Good to know this stuff. And again, another reason you're going to want to know which ones these are is because they're going to be the ones that are listening to that traffic on that multicast, the 224.0.0.6. And I think it was actually, .5 up here for the hello packets. .6 is actually unicast, I think. I think this is unicast. Look into that. I make these notes for myself, and I actually do look into them, so good stuff to do. And this is the traffic for link state. Yeah, just keep reading my notes. Jeez. Changes to the network. So this completely makes sense, right? If we remember, link state was the changes to the network stuff. The LSA is the LSA acts. So it makes sense that you'd want your designated router and your designated backup router to be the ones listening to those changes and updating everyone within that multi-access segment, because they're the ones that are also going to be sending out the hello packet. Amazing. It all comes together. So in a multi-access, that means that the DR is going to be the only router sending out multicast hello packets, etc. Whatever else might be going out on this on the 224.0.0.5. Because we were just talking about this. So this limits how much traffic is going out from all these routers on this spider network. It keeps it down. So it's only one router sending out these updates, and it's within this entire, what did we call it? Multi-access segment. So again, this is only if you don't have router-to-router connection, right? That's what a multi-access segment is. It's outside of a router-to-router connection, interface to interface from a router-to-router. If you're doing interface from a router to an interface on a router, none of this multi-access stuff matters. And that's why if we go up here, it's if exists, right? So within the hello packet, if it is a multi-access segment, then this is going to exist. It has to exist. And it's going to be designated by the router ID because they all default to 1. Cool. Neat stuff. Where else do we go with this? Okay, so we were going to talk about areas, right? This is something we talked about above that's only used on large networks. So up here we said, again, area ID. On a small network, you're just going to use one number across your entire network, and typically you use 0. But you can use any number. You just want it to be the same number. But larger networks, again, for the same reason that we designate like a designated router within a multi-access segment, is kind of the same reason that we have areas. It's to keep traffic to a minimum across the entire network. It's just to keep it segregated within areas and then allow those areas to communicate with each other. So this is how that works. Ospf areas. So something to keep in mind, areas only work if you also configure routing summarization across your network. So it relies on routing summarization to work between these areas. So that's kind of how you keep it segregated, but also keep the information pointed in the right direction, is by summarizing your routes and then pointing towards that summary instead of to all those individual routes. So you can see that has one route to go to versus how many ever would be on that area of the network. And that has to do with subnetting. We touched on that earlier. I'll do a review of that at some point as I'm going back over this material. Honestly, I wish I understood it better to the point where I could just like talk about it, but I don't have any notes on it right in front of me, and I don't want to mess it up and put misinformation out of there. So moving on, the OSPF areas, continuing on the OSPF areas, but outside of the routing summary, we're going to talk about how it's a 2-tier system. Let's move this entire thing down. What is it? Controller? No, that's not it. 2-tier system. So tier 1, the upper tier, is going to be, where are you here? The transit area. So if we want to compare this to how yesterday we learned the spine leaf, the transit area would be the spine, and the regular areas would be the leaf, if we were comparing it to that. And the transit area, the upper area, so much like the spine, is the backbone and does not generally contain end users. No end users are typically connected into this segment of the network. So this is upper stuff. This is we've already done everything that we needed to the end user data to shift it, and now we're just looking at speed and durability at this level. And then tier 2 is your regular areas. So like it implies, this is where we're going to be connected to end users. So this is used to connect end users to the transit area, the area above it. So this is just a layover between the end user and the top tier. So here's where it gets a little wonky because it's a 2-tier system, but there are technically border routers which aren't in the tier. I don't know, man. I don't know why they aren't counted as part of one of the tiers, but we got ABRs, and these are area border routers. Area border routers have a foot in either tier. So they got one interface in tier 1, and they got another interface in tier X, X being any other, wait, no, is that right? Nope. Scratch that. Tier 2. I was expanding a little too fast there, right? Area, regular area. No, because there could be more than one area. All right, I'm going to scratch this all the way back. All right, so the transit area is also known as Area 0. Blah, blah. And then the regular areas are going to be areas where end users are connected, so there technically can be more than one, and they're going to be labeled as they are. So Area 1, Area 2, Area 3, and these are going to be segmented areas of the network. So typically they're also going to coincide with like if we're building this network out, we'd want it to also coincide with different. We'd probably want it to be like different sections. So Area 1 would be like also be like either a building or like maybe even on a section within that building, like accounting or something like that, so that we could area that off. But now I'm talking a little bit beyond what I should. I'm getting a little out there. Okay, so what do area border routers do? Area border routers sit between 2 tiers. So they have, like I was saying, they have a foot in either tier. One interface. Oh, you know what? Instead of saying tiers, let's say areas. Sit between 2 areas. Oh, that's so much better. And that will make more sense, kind of make more sense as we get a deeper understanding of this, because technically you can have more than 2 areas on a router. It gets real. Man, I don't know. We're working on it. So it's going to sit between 2 areas. It's going to have an interface connected to, for example, area 0, and another interface on that same router connected to another area. Just another area, because we don't know what it would be. Typically 1, but who knows. But it should be connected. If it's a border one, it should be connected to the transit area on at least one of its interfaces, right? Because it's bringing you, it's a border between the transit and then just another regular area. But it could be more than just, you can have like 7, 8, 9, 10. I don't know how many areas you can have it on a network. It's supposedly a lot. So we don't know what the number would be here. It's going to be above 0, because it's not going to be your transit. You're not going to put a border between 2 transit routers. That would just make it a transit router. If you can follow that logic. ABR, separate the LSA flooding zones. So we learned about LSA yesterday. That's the link update. It's telling them, this. I'm getting this interface is down. We need to redo these routing. We need to redo our routing tables. So this is a way, like we were saying above with hello packets. This is a way of segregating our network so that it's not being cast. You can see with how, like, a large network, if you're if you had a single zone and you were constantly getting these floods of LSAs across the entire network, how that would, even if you had designated routers within your multi-access segments, it would still eventually overload your bandwidth, right? Like, it'd overload a network. It's unnecessary bandwidth usage. So that's what we're trying to prevent with areas. And again, this is only for large networks. So this isn't something that you have to worry about if you're on a smaller network. So it separates the flood zones. It's the primary point for area address summarization, which makes sense, right? Because if you're pointing one area to another area and you're doing it through a summary route, you're not advertising all the routes on that router. You're just saying, hey, if you go to this route, you can reach all these different routes. So you're just pointing it to one thing. So again, if this is the router on the border, this is the one that has the interface on either side, it's going to be the one that you want to have all those summary routes onto that you can point to, because it's where it's going to be going through, right? So you're going to point it to the interface on the opposite side of where you're coming in. And that's going to be your summary route. You're going to say you're going out there somewhere. And that's going to be the next area. It makes sense. It does. Functions regularly. As the source for default routes. So again, this is where you're going to be setting up default routes if you want, like, one setting a route to, like, outside your network, so your ISP, a default route to your ISP. That's what that would be. There'd be other reasons to set up default routes based on your network, but this is again where you'd want them, because it's sitting between the 2 areas. Maintains the LSDB for each area it has an interface connection to. Oh, this is interesting. So link state database, right? So this is one of the only routers that's going to have network topology on area 0 and the other area it's connected to. Area 0 isn't going to have full network topology on area 1, right? Because it's not directly connected to it. It's going to have only that summary route. So it's going to know there's a bunch of different networks over there by the summary route, but it's not going to have the full network topology. It's only going to have the network topology of area 0. And that's, again, so that's to keep all the unnecessary broadcasts down. However, these ABRs, these area border routers, are going to be the ones that have like kind of the more in-depth understanding of your network. They're still maybe not going to see all of it depending on how many areas you have, but they're going to see more than your typical router in this setup. So that's another reason to keep these routers secure, probably, because they're going to have that much more information. And it's also important to know because that's, based on like for the exam, based on some packet they show you, if it has a bunch of different like areas in it and stuff, you're gonna be like, oh, that's probably like an area border router, that kind of stuff. So again, I was talking earlier, ideally, you only want an ABR to be connected to 2 areas. Typically, you always want one of those areas to be area 0, your upper tier, your transit area, right? And then something else. However, you can connect up to 3. You can have up to 3. But after that, it just fails to work for whatever reason. He didn't actually go over why you can't have more than 3, but you can only have 3, so don't be going over that. And if you have a larger network, it should be easy to do that. Hopefully, if you have a large network, you're not like really hurting for an additional router to create that bridge between between areas. So there's one last type of OSPF router. It's the ASBR, the Anonymous System Boundary Routers, Autonomous System Boundary Routers. Is it anonymous or autonomous? It's anonymous. Okay, checking my notes. I'm racking my brain, and I honestly don't remember what I learned about these. These are routers that are redistributing another routing. Oh my goodness, that's right. Okay, so and this is why I don't remember, because it's super obscure. So in the off chance that you find yourself running more than one protocol, and those protocols are meeting in this kind of area interface that you have set up, then you're going to want one of these set up on, just like you would set up an ABR, only this one's going to have 1 foot in your area, so it's going to be running OSPF, because that's what we're talking about. This entire thing is OSPF routing, so it's going to have one interface running OSPF. So one interface is running OSPF, and another interface is running some other routing protocol. So that could be IS, that could be RIP, and that could be the Cisco one, which I can't think of the full name of it. Was it in yesterday's notes? Oh, I don't see it in yesterday's notes. Okay, that's okay. EGR, you know what I'm talking about. Yesterday's notes, the other protocol. I shouldn't have brought it up, man. I didn't know it for sure. Oh, I don't know if it's in these note cards. It may be in the ones in my room. I don't think it's in these note cards. No, this looks like it's gonna reach to that, but it's deeply in my brain now. No. I'm gonna find it just to prove myself that I can. What day were we talking about that? Wasn't it? If it wasn't yesterday, it must have been the 1st. EIGRP, Enhanced Interior Gateway Routing Protocol. We got there eventually. Let's type it out. Enhanced Interior Gateway Routing Protocol. So I didn't need to go through all that. I could have avoided that. But again, an ASPR, an anonymous system boundary router, is going to be one that has one interface running OSPF, and that's going to be running into an area, because again, this is all, we're talking about areas, we're working within areas. So that's going to be running into that's not going to be running into your tier 1 transit area, more than likely. It's gonna, well, maybe it would be. I don't know how this would be set up, honestly. It's a very uncommon to do, but one interface would be running an OSPF area routing protocol, and another interface on that router would be running one of these other protocols. And thus it would be in an anonymous system boundary router, because it would have to translate between those routing protocols somehow. And I don't think he actually went over how that would happen, but you know, sometimes you learn in stages, and that's not something we need to know yet, I guess. So again, this is just like the ABR is representing a boundary between area 1 and area 0, or area 0 and area whatever area it is. The ASBR is also representing a boundary, but instead of between areas, it's between protocols. So we know for sure one is going to be OSPF and it's running areas, and the other one is going to be another protocol. I think you're probably not going to need to know a ton about that. You're just going to need to know what they do, like not necessarily more than that, just because it's so obscure to set up an ASBR. I certainly hope I don't have any questions involving it, unless the question is like, what router type would be set up between 2 protocols? And I'd be like, ASBR, don't ask me anything else. don't go in any more depth, please. But we'll get there. So let's go over OSPF cost metric, right? So why is OSPF chosen? How does it calculate these costs? Well, the costs are speed, clock rate, and bandwidth are 3 ways that OSPF can determine the cost. So that's speed, clock rate, and bandwidth. And we can actually manipulate these as network administrators. So speed can change the speed of transmission. We can actually enter in the speed, and that speed will actually affect the speed of transmission over that line. So if we wanted, we obviously can't like speed it up past this theoretical limit. So if you have a 100 megabit connection, you can't put a speed of 1 gigabyte and expect it to go faster, but you can narrow the speed, right? So if you have a 100 megabit fast Ethernet connection, you could make it a 50 or a 10 or whatever, you know, you could pare it down. You can also do the same thing with the clock rate, so you can change the speed of transmission. So it's important to note that this one is in megabits per second, right? So like most internet speeds are advertised megabytes per second, but the clock rate is in not kilo, giga, right? Gigabits per second, kilobits per second, gigabits. Man, one of those two. So this is for serial ports. This is not common, but if for whatever reason you are connected over a serial port and you want to pare that speed of that serial port down from 1.55 megabytes, something like that, 1.52, 1.55 megabytes a second to something less than that, you can do it. And we'll go over why we'd want to do this in a second. This is just kind of giving you what the cost metrics are and how to manipulate them. So the last one is bandwidth. So the important thing to know about bandwidth is it does not actually affect bandwidth. You can change the number, so it's 100. If it's 100 megabyte connection, megabyte per second connection, like a typical fast Ethernet card can go to, interface can go to, you can change that to a 10. It will still run at 100. It will still be able to run at full bandwidth, unlike if you were to change the speed where it'd be limited by that. So it can still reach its theoretical limit, but it's listed as less than that, right? So this one these two we actually changed the speed. This one we list the speed is changed, but the speed is not actually changed. So that's important to realize. So again, speed and clock rate, we actually changed the speed at which this line runs within OSPF. But with bandwidth, we only change how it looks to run. So as OSPF looks at it, it looks like it runs slower than it actually does, but it still runs that fast. So why would we, let me see if word cost overrides the actual bandwidth value without changing bandwidth. Yeah, I just went over that. Sorry, I was just reading what I literally just said, and for some reason that broke my brain. OSPF reference bandwidth. Okay, yeah, so I understand what I was trying to say. So OSPF is not a new protocol, right? So when it was put into place, 100 megabyte per second connections were like, what? You're rocking it. But now we got like 10 gigs, right? Which is like, that's 10 gigs? No, that's 1 gig. That's 1 or 10 gigs. So it goes a lot faster now, right? Regardless to say, network speeds have increased, right? But the default, what OSPF was programmed as, was that everything, this was baller. This was the best you could do. So it divides all network speeds by 100 because it thinks the best speed you could possibly have is 100. But we know it's not. So what we can do, we can put, I just went over that. So OSPF treats all interfaces of 100 megabytes per second or faster as equal, right? So it'd be a cost of 1, because no matter how much faster you're going than 100 megabytes per second, you're not going to get like a decimal point answer when you divide 100 into it, right? Or that number into 100, because that's how you get the cost. Did I go over that? Yeah, I kind of did, but I didn't really. So the default is taking 100 and dividing the speed of the line into that, and then whatever you come up with is the number that you associate with that line, and then OSPF bases that number with how well it's how high it gets on the routing protocol and the routing table. Man, today is rough. So that would mean that anything above 100 megabytes per second would would be a decimal point and they'd automatically be shifted up to 1. And we don't want that because we clearly want 10 gigabyte connections, or, you know, it could be faster by the time you get a networking job. By the time I get a networking job, it could be much faster. Who knows? We don't want those to be associated with 1 gigabyte and 100 megabytes. So what we can do is we can change the we can use that bandwidth command to so instead of that bandwidth command right here, so where were we? Bandwidth. It does not actually affect the speed. Hey puppers. So we can change the bandwidth number, but it doesn't actually affect the speed. So what we can do, we can use that bandwidth. Man, I'm repeating myself. Command to push the reference value higher. Man, my notes sound way better than I do right now. So we could just pretend to run a little thing here. Boop, boop, boop. We're in privileged executive mode. We're going to type in router OSPF1. That's starting OSPF on that enter, I think. Router 1 config router. We're in router interface, I guess, or router configuration, global configuration. I don't know where we are, to be honest. We're gonna do auto cost reference bandwidth. Oh no, that's not an underscore. The bandwidth, and we're just gonna put a huge number in there. So the thing about this though is we have to do this to every single router. Like, there is no command that we can push out across all routers that I know of yet, which is a bummer. We wouldn't technically have to do it to all routers. We'd have to do it to all interfaces running OSPF, which probably would be all routers, but you never know. And maybe we learn like a way to put it into an API or a batch to send it out over all of them, like a control unit that you can do that with or something. That'd be neat. But basically what this would do is that would change the reference value from 100 to, in this case, what is that, 100,000? And so that would make all the numbers adjust accordingly. So this would work for things well past 10 gigabits, clearly. But that means, because you have to change it on every router, you don't want to have to put it at your limit for that day, right? Because you may upgrade within the next couple of years, and you don't want to have to go back into all your routers and change that reference bandwidth again. So when you're doing it the first time, just put a high number, man. It's not going to change much. It's not, you know. Seems like it's only going to help you. I'm sure there's a theoretical limit. That's why I'm kind of putting that caveat there. Like, I'm not just saying like go wild with it, because I'm sure if you put too high of a number, it cause some like buffer overflow issue or something like that. People be like, why do you say that? Why that kid that knew nothing except for what he studied that day? And why did I take him at his word and destroy this multi-million-dollar network? Perhaps I'm worried about something that's not going to happen. You know what? Do we want to start? Let's not start enter Vlan routing. I didn't get that far into it anyway. So we're tomorrow we're gonna start enter Vlan routing. So we already went over Vlan routing a little bit. This just has to do with a little bit more in depth with trunking ports and allowing VLANs to communicate with each other. Was the gist I got from what I was able to study today. Was allowing it inter VLAN routing is allowing VLANs to talk to each other. That should be pretty understandable just by the name to me. But it also uses truncated ports. Trunking ports or truncated ports? Got to get that vocabulary. Truncated sounds better for some reason, but I suppose they'd be trunking. I don't know. Anywho, that's let's kind of review a little bit trunking versus access, what we think of like branches versus pushing a bunch of VLANs over one. Was it one line? I think it was one line. I can't remember. It's been a long day. Appreciate everyone. Appreciate it. Appreciate just coming by, stopping by. I know today was a little wackier, a little looser than typical. I apologize for that. I am running a little zany as we get into these things. I am looking forward to my new resources coming. Psyched about that book. Get some more sleep. Also excited to see the government tackling technology, tackling inequality at the same time. That's pretty cool. Excited to see more people get access to the internet, access to computers and technology and all the wonderful stuff that I play with on the daily. So that's all really neat to me. And again, tomorrow I'm going to start Enter Vlan Router. And that didn't seem like a huge section, so we'll probably go on as far from there as we can. Until tomorrow. Thanks, everyone, and have a good night.